Hi, we are Team Formula152, and this is our MAE152 project, where we will be analyzing different components of an FSAE race car.
I'm Chris, and I analyze the exhaust headers running from the engine, which carry away hot exhaust gases. The exhaust can see acceleration and static loading, while engine vibrations can cause resonance, which require a complete modal analysis. The exhaust was analyzed with 3 iterations. One is the original, the second is a thickness increase, and the third is a tube brace. The first analysis was a 50G impact to simulate a head-on crash. Both design iterations reduced displacement, but increased maximum stresses for boundary condition 1. The second analysis was a 50G impact to the side to represent a side crash. Both iterations increased performance, but the brace was ideal for this case. The third analysis simulates a tool dropping on the exhaust. Both design iterations improved performance, but the thickness increase was the best design. A modal analysis was performed in the exhaust. The first resonant frequency falls on 630 Hz. However, engine vibrations should not exceed 550 Hz, so resonance will be avoided. A fatigue analysis was performed using the worst-case stress of 100 megapascals. For this scenario, the exhaust can withstand up 10 to the 7th loading cycles, which is sufficient for a 10-year lifespan for a car.
I'm Matthew, and I analyzed the front upright of the vehicle, which are used to mount the wheel and brake to the suspension system. The upright was machined from a block of 6061 aluminum, and the upright may experience static loading resulting from an impact or bump force. It may also experience vibrations from the road. For the first analysis, a 78.5 kilonewton bearing force was applied rearward to the inner ring to simulate a front wheel impact. Both design iterations saw a reduction in displacement and stress. For the second analysis, a 1500 newton bearing force was applied to both caliper tabs to simulate the loading they would experience during braking. The first iteration sees the same displacement and worse stress, but the second iteration sees an improvement in both stress and displacement. For the third analysis, a 3000 newton bearing force was applied upward to the inner ring to simulate bump force. Both design iterations see an improvement in both stress and displacement. For the vibrations, I completed a modal analysis to determine the resonant frequencies for the component, and I found that the resonant frequencies are much higher than those it will experience, so it is unlikely to be an issue.
I'm Natalie, and today I'll be discussing the FEA analysis of a Formula SAE brake rotor. The goal of the simulation was to evaluate the rotor's performance under different loading conditions, including braking torque, tool impacts, thermal effects, and modal vibrations. We conducted multiple iterations, starting with a base design, increasing thickness, and adding cutouts to assess their impact on stress, displacement, and overall durability. For all our analyses, we used two boundary conditions. Both of them have the 6-button screw hole fixed. The first one has the caliper contact area on rollers, and the second one has the caliper contact area fixed. The first analysis focused on braking torque, as the rotor experiences significant stress during deceleration. According to the FSAE rules, the rotors should withstand a braking force of 2,000 newtons, so we decided to simulate the effects of a 3,000 newton force, which in turn would give us a 270 newton meter of torque for our application. Our results show that increasing thickness reduces stress by 25% and displacement by nearly 40%, while adding cutouts increase displacement slightly. This balance between strength and weight savings is crucial for optimizing performance. We also analyzed tool impacts to simulate accidental drops or strikes during maintenance. The first impact case involved a radial load. The results indicated that increasing thickness reduced stress approximately by 20%, while displacement improved by up to 28%, while adding the cutouts increased both the stress and displacement. This suggests that a slightly thicker rotor could better withstand accidental tool contact. We simulated a tool impact normal to the rotor face. This test showed that stress was significantly reduced with the modified designs, particularly the thickness increase, which lowered stress by 37%. Displacement also saw major improvements, making the rotor more resistant to localized damage. Thermal performance is critical for brake efficiency. Our analysis applied a 10,000 watt per meter squared heat load with convection effects, revealing a peak temperature of 180 degrees Celsius. These temperatures were applied in a thermal loading analysis with the mounting points fixed. This caused an extremely high maximum stress of 1,260 megapascals, which would yield and likely fracture the steel rotor. This was found near the fixtures. However, this high stress is likely unrealistic due to the boundary conditions which prevent the brake from expanding. In reality, the brakes are clamped and not fixed, so these stresses would not be as high. Finally, modal analysis ensured that the rotor's natural frequencies wouldn't interfere with normal vehicle vibrations. Our results showed the lowest resonance mode at 1,279 Hz, well above the typical suspension and tire frequencies of 50 to 200 Hz. This confirms that the brake rotor will not experience unwanted resonant vibrations during operation.
This is the closed-form solution for the rotor. The theoretical maximum deflection and maximum stress are less than that of the simulation. This is because the theoretical calculation is not taking the fixtures into account, which will influence these values. Hi, I'm Terry. I analyzed the chassis of the FSAE car. The chassis is manufactured out of 1020 steel tubing and is MIG welded by the students. The chassis can experience intense crashes and must be able to protect the driver. The chassis was analyzed through a front collision, side impact, and in the case of a roll, through static simulations. The first analysis was a 33,000 newton impact to the front of the car. The second design iteration greatly increased the displacement and stress, which reduces the effects felt by the driver. The second analysis was an 11,000 newton impact to the top of the car simulating a roll. The chassis performed great with the base design deforming the perfect amount to protect the driver. This left small changes to displacement and stress with each iteration. The third analysis was a 33,000 newton impact to the side of the car. The first design increased displacement and stress, reducing the effects felt by the driver. The race car will experience frequencies of 3 to 300 Hz on the racetrack. The actual resonant frequencies will be much higher than these values listed in the chart, allowing the race car to perform on the track. The chassis will be weighted down by the driver, engine, etc., and it is made out of tubing rather than beam elements. The solid brick simulation would only work if we treated the tubing as beam elements, therefore reducing the resonant frequencies.
In summary, our FEA analysis provided valuable insights into how our different FSAE race car components respond to mechanical, thermal, and impact loads. The design iterations helped reduce stress and displacement while maintaining durability. These findings will contribute to optimizing our design for improved performance and reliability. Thank you.